and today's lecture will be focusing on plant modeling in frequency domain. Okay, first of all, why we need to do modeling is that in control system design, the main objective is to find the output transient of the response of the systems, meaning that if we were to design systems, okay, control systems, right? So let's say this is control systems. So we need to be able to determine what is the response of the output of the system. Let's say we provide some inputs, step input. Then we need to see how fast the output responds to the inputs in terms of three things. Yeah, first one is the transient response, and then steady state. So we need to see how the control system behave when the input is given, and then it will we need to observe what is the behavior of the outputs. So in order to do this, we need to model the system. Okay. All right. To model the systems, we have to be able to analyze it. So that means the system has to represent by some transformations, right? So if we have a physical systems, let's say we have a car suspensions with absorbers and let's say there's a tire, there's the body of the car. So we need to represent this system into a model so that we can analyze it in terms of, okay, in this case the input is the road surface, that's the input. The output is how much the distance between this body moves, we call x. Okay, so when the input provide to the system, these systems, so we need to see what is the response of the x, the displacement. All right, so we need to be able to come out with some models. So that's the reason why we need to do the modeling. It can be in the time domain or frequency domains, but in these lectures we will cover how to model a system, a physical system, into frequency domains. Okay. What is transform? Transform is a mapping between a set of data or domains. Usually when the data is transformed to one domain, it can be transformed back to the original domain using inverse transform. So if we transform this into whatever domains, we should be able to transform back to the same domain, right? So it's always two-way transformations so that we can go back to the original design. Okay, the transformation is, the main purpose of transformation is to be able to see different parameters. That's one thing. So certain domain we can see, like in time domain, we don't see certain things that we can see in the frequency domain. Same things, even in the frequency domain, there's something that we cannot see from the frequency domain perspective. We have to convert back to time domain to see it. So the idea is that to change between the models so that we can analyze the system in a effective way, easiest way, and so that the system can be visualized, can be analyzed easily. All right. Okay. Why we need to transform? Because based on the time domain, is the system will be a bit complicated to analyze because we have to consider the changes in time domain. That's why we need to convert to see from different domains so that we can see different, like I mentioned earlier, different parameters. All right. Okay. Okay, just for a quick example here. So if we have a transmission system, suspension systems, we will expect the systems. We will expect the system's response to be stabilized after hitting a bumper, for example. So this is at equilibrium positions, and then when it hit bumpers, it will provide some transient response, and then after sometimes it will come back to the normal, right? So the system that we represent should be able to give us some information about how fast the system stabilizes, how fast the absorber system stabilizes, what is the times it takes to stabilize, and then what is the overshoot, all these things. So we can see it in very detailed so that we can analyze from the model, right? So that's one example. The second example is let's have a look at the water heater systems. So normally when we use the water heater systems, we need to turn on, of course, we need to set the temperature. Okay, when we set the temperature, the internal controller will try to regulate, okay, from whatever, just forget about these numbers. So whatever actual temperature, right, maybe our ambient temperature is 27 or 30 degrees. So from 30 degrees, we need to raise up to 60 degrees, for example. So we set this here to 60 degrees, and then the system will regulate and then try to bring the water temperature into, so the water temperature to the desired temperature. Okay, let's say this is water heater system, right? This is the input, this is our set temperature, we want 60 degrees C, and then the output is not immediately reach 60 degrees, but it takes some time to reach 60 degrees from 30 degrees or 60 degrees. So this is what we call transient response. This is we call steady state response. Okay, transient response. This is steady state. This part here is steady state. Steady state response. Okay, that's what we need to see. Okay, for the third one, because different example will produce different response. For suspension, we want the system to come back to the original position, to the equilibrium positions, but the temperature when we set, we need the system to regulate to the desired temperature. Okay, for drilling system, we don't want the system to overshoot, because if we set a certain depth of the holes that we need to drill, so the drill will slowly reach to that point without any overshoot. So it will slowly go and then stops and then stabilize at that. Let's say the maximum we want to set, we set to 10. So this drill bit will actually drill a hole until 10 without any overshoot. That's the response of that, the distance of the drill bit. Okay. For baby swings, for example, we would like it to swing forever, because so the response will be like similar like this. Okay. So in these four cases, we could say that any system is designed according to the requirement. Okay. So it doesn't mean that this response is good, this response is not good, but it depends on the application. So if the application requires like this is good, but we need to ensure that how fast, okay, how fast this drill bit reaches 0 to 10, let's say 10 mm. So how fast? So we should be able to see it. All right. So based on the example above, the output of the output of system response of any control system can be divided into four. Okay. So the first one, you see that it is it's like a sine wave. So it happens when the damping ratio is 0, zeta, this the zeta symbol. So when there's no damping, the system will oscillate forever, right? It's like there's no friction. So if we swing something, baby swing, for example, if we swing, if there's no frictions, there's no damping, there's no air friction, nothing, there's no losses, it will swing forever in ideal case. So we want to be like that. So the second one is critically damped, which is zeta equal to 1. So that will actually suit this purpose. So it's under damped, zeta falls between 0 and 1. So there's some, you see some like this, some oscillations, and slowly gradually dies out and then stabilize at certain point. So what we call underdamped, and underdamped systems, this undamped I just mentioned earlier, this is undamped. Overdamped is zeta more than 1. That means the very high frictions, could be 10, could be 20. So the system it takes time to reach the final state position. Okay. So we need to go back to how we can understand why we use Laplace to represent the systems instead of other method, right? So some reviews about MATLAB and Laplace and Fourier transform. Okay, if let's say we have this is a signal, right? Functions in sine terms. So it's a continuous signal, so it will be represented by Euler equations here, and then that represents the whole system, the undamped systems. Okay, so sine wave. We have another signal called exponential terms, which is e to the minus sigma t. It's converging signal. If it is negative, then the system will die out over time. So we have these two signals, right? So we can see that if this signal and this signal combine, when t approach infinity, the system will actually get into one stabilized state, right? So that will suit this application. So whatever signal that we have, continuous signal, if we include the damping or converging signal here, then the system will die out. All right. So there are other transformation as well, but as far as this course is concerned, we are actually focusing on Fourier and Laplace transform, particularly Laplace transform, because it suits to this control sort of framework. Okay, that's a Fourier transforms. Any time domain function ft, we could transform to Fourier transforms to f to omega, and we use that functions. Then we could transform to that, and then the same thing we can transform back to the time domain using Fourier inverse transform. Okay. All right. The good thing about Fourier transform is that any periodic waveform can be found using a building block, simple building blocks. I mean, any signal, a continuous signal, we could find a combination of signal that make that final signal, right? So this is the Fourier transform of ft. Then we can have this, right? Okay, if we want a continuous function ft that dies out over time as in the physical world, because anything in physical world will dies out over time, then ft signal can be multiplied by a certain converging function, which is with damping factor, as shown below. So which is ft, example, ft equal to a dot e to the minus delta sigma t. Okay, this is converging functions where e to the minus sigma t is a damping factor or the rate of ft converge or dies out. Example, 5e to the minus 2t. We have 5 f of t, 5e to the minus 2t. Then the signal becomes when t equal to 0, t equal to 0, and then t approach infinity. Then we will have something like that's 5. When t equal to 0, the amplitude is 5, and then it takes time to slowly, gradually dies out depending on this, right? So and then if we combine this with Fourier transform, where Fourier transform only consider the imaginary parts, which is j omega t here, because it is a continuous periodic signal. So and then we combine this with the real parts here into Fourier transform. Then it becomes Fourier transforms that takes the input of sigma and omega, then becomes the Laplace transforms. That's how Laplace form is transformed, because from here and then it will change to S domain, because where S represents the sigma and omega, right? So instead of using this Fourier with a real converging factor here with sigma and omega here, then Laplace came out with his own F cross S using these transfer functions, where S is a point on S plane, S equal to sigma plus j omega, right? It's the same thing, but represented by S. S can be real, complex, or imaginary. So in this case, S can be 0 plus j omega t, which is imaginary parts, which in fact is belong to the Fourier transform. The system is equivalent to Fourier transform here. So if S equal to there's a component real and only real components, then the system is having a constant damping like this. If S equal to sigma plus j omega, which is complex, the system having both constant and oscillation damping, right? So the S can be of these three, and then we'll need to see what is the how do we transform that. So this is just a Laplace transform. So wherever time domain function, we just use this transform, add this function into ft, and then we need to find this the Laplace transform. Okay, example, we have f of t function in time domain e to the minus at ut. So if we transform this, we use this Laplace transforms ft. We put ft, which is ft a to e to the minus at. We substitute that value inside there, and then we get this. Okay, so from f of t equals a e to the minus at ut. Okay, then if we Laplace this, f of t equal to L of s. Okay, this is equal, no, sorry, f of s equal to a over s plus a. So that's a goes here, that's this a small a goes here. So if we have 5e to the minus 10t ft, then we can simply convert that to f of s equal to 5 over s plus 10. Okay, then similarly, if we have f of t equal to 10e to the minus 5t positive, yeah, so then we can have a Laplace transform f of s equal to 10 of s minus 5. So basically we don't have to really derive one by one. We see the pattern and then we can straight away transform them into Laplace form. Okay, that makes our life much simpler. All right, if we have, for example, we have a time domain function f t equal to t, then we can convert that to Laplace s domain equal to 1 over s squared. F of t equal to 5, we can Laplace it into 5 ut. Alright, so you can follow this table. Okay, ft sine omega t and Laplace s, then it becomes here omega over s squared plus omega squared, meaning that if we have sine 10t, then we can have 10 over s squared plus 10 squared. Alright, so that's in Laplace. Simple, isn't it? So so that this is the table, so we can refer to this table. Okay, we don't have to really derive it. That's not our topics to discuss here, but as long as we could refer to the table and convert that into Laplace domain, then should be okay. All right, the next one is we could use Laplace theorem table here to transform the time domain function into frequency domain. Okay, for example, for linearity theorems, if we have 5xt, okay, 5x of t, then right, ft equal to 5xt, we could convert to Laplace f of s equal to 5x s. So you just capital the x and then replace t with s. Yeah, if we have f of t, then x1 t plus 25 x2 t, then we can Laplace it. Okay, f of s, we can simply use these linearity theorems here, right, to transform to this frequency domain, which is in this case 10 x1s plus 25 x2 of s. All right. Okay, for differential theorems, this is for linearity theorems. If we have these terms in our function at the time domain functions, then we can simply convert that. For the differential theorems, if for example we have 10 d x of t over dt, then we can find the Laplace transform to 10 s x s. Just add an s for the first integration. First integration. If we have a second integration, f of t plus 5 dx t over dt squared, that will be f of s 5 s squared x t. So we just add this for the second derivative. Okay, second derivative. First derivatives we use this s, second we use s squared. We just follow this differentiation Laplace theorems table. Okay. Okay. Take note that we don't use these initial conditions here. We just base on this, right? Okay. The rest you can refer if I think these two are very useful for the control system. The rest we don't really use it much. Okay. So we do some example here. I think I just show you the example. If f of t equal to kxt, then maybe convert that transform to Laplace becomes f of s kx of s. Right? We use that theorem, this linearity theorem. All right. For in case of fv dxt over dt, so we have this same as this. All right. So and then if we have this, then it becomes like this. Okay, fine. All right, just some example here. Transform ft into Laplace domain. Ft, if we transfer to Laplace domain, become fs. F prime t into Laplace domain become s of s. F double prime t into Laplace domain become s squared f of s. Yeah, s squared. So transform f of t equal to e to the t. We can have this 1 as if we have, I think I didn't mention it earlier, f of t equal to e to the t. All right, then we transform that Laplace f of t equal to s, no sorry, f s equal to because it's 1, this is 1 over s, because this is positive 1, right? So s to the minus 1, right? So this is the system. Okay, so same things here. You got this, all right? Okay, let's do some practical example here. Let's say talking about suspension systems, we have a model of systems which consists of springs, damper, and mass. Then this ft is our input. This is the motions, displacement of m. Okay, so we have this. We can derive a model, B, right? K for springs, B for a damper, M for mass, and then Ft for input, Xt for this one. Okay. Then we can say that we can use this Newton second law of motions, where we can use the free body diagrams. So this is free body diagram. So using the vector, so this is f of t. There's a force, pulling force this side. So the rest of the force is actually facing opposite sides, which is the m itself, which is m. Because using f equal to ma, we can have d squared x of t over d t squared, right? This is f equal to ma, second law motions. So then we have one that's the opposite force k, which is k x of t. And then damper, we can use b dx of t over dt. Okay, now we can write differential equation, the modern in differential using differential equation f of t equal to m d squared x of t over dt squared plus b dx of t over dt plus kx of t. Okay, all right. In time domain, the equation is a bit like you can't actually imagine what is the parameters, what is the response of the system, because you need to actually consider every single t from 0 to infinity, right? So that you can see the response of the systems. We need to see the response of the system. So every t equal infinity, so we need to substitute so that we can find what is the magnitude of xt. All right. So now using the previous theorem that we have, we can change, you can Laplace this Laplace ft, right, equal to fs, because this is the differentiation theorem from the table above. Right, from here we can see that differentiation theorems, so we can use that, which is m s squared x s. It's on the same thing, b s x s plus this one is linear theorems, k x s, right? So maybe I'm writing too big, sorry, but okay. Okay, we have f of s m s squared x s over this one, plus b s x of s plus k of s, kxs, right? Kxs. Then we know that fs is input, xs is the output, right? xs, yeah, all xs is outputs. Then we can produce a transfer function that represent the systems, which is the output over input, which is the output is xs. We need to find x of s over f of s equals to 1 m s squared plus bs plus k. So this is the system model in Laplace. Yeah, this is in Laplace form, frequency domain, right? So it looks much simpler than the time domain here. All right. Okay, that's another example that you can try. Um, you can try for RLC network as well. So that will produce both. One is the time domain function, and then we will convert that to frequency domain functions. Okay, at least we can discuss this for systems that consist of mass spring damper. This is also mass spring damper, but it's rotational systems. This is resistor, inductor, capacitor, RLC network that represent the electronic systems. And the last part is electromechanical DC motor that consists of electronics and some mechanical systems, rotational system that we can find this. Okay, so any system we can model it so that once we model it, we can control it. All right. I hope you can try these four at home. All right. Please derive, understand. Please derive yourself and understand how to transform into Laplace domain. Okay, so you need to try this. Okay. Okay, there's plenty of information in the book or internet how to transform this, but you make sure that you know how to do it. With that, thank you very much.